Okay, cool. All right, thanks for that, Joe. So yeah, I'm pretty excited to be here. I'm based in New York, along with my team, my company. I've been sort of going to the New York, variant of this for pretty much the whole time I've been in New York, so good like 2.5 years at this point. And as much as I miss that group, it's kind of nice to be able to sort of travel the states a little bit, meeting other Rust meetups because they're always really nice communities. Um, so I'm Sam. I'm the CTO and co-founder of a startup called Oso. As I said, we're based here in New York. Before I was doing this, I did a PhD in cryptography, and that's kind of my background. And I spent a big chunk of that, first picking up Rust and then like implementing a bunch of my like random crypto things in Rust. Is a really nice language for that, and that's kind of where I really got pretty fanatic about both Rust and security. This is the Oso team and the sort of Oso extended family, minus a few people who you didn't get into the photo before COVID times hit and we can't meet up like this anymore. Okay, basically what I want to do in this talk is, first of all, I do want to show off Polar and Oso, which I'll explain in a bit, mostly because I just think those are really cool. And you'll see what those are in a bit. But the sort of Rust specific piece of this is, so a lot of this we built in Rust, and I think there's like lots of parts of the stuff that we had to build which are just kind of genuinely interesting in that we had to do some stuff that most people maybe wouldn't have encountered. So we kind of hit some of the strange corners of Rust that you might not have seen. I think those are kind of fun to share. But for the second goal in particular, like please do feel free to like stop me at any point, ask me to like dig a bit deeper or explain something if there's something that I've kind of breezed through and not really given enough chance to explain, because as I said, I want to show off Oso because I think it's cool, but I want everyone here to get something from this and learn a bit about Rust. So basically, I'll give an overview of what this Oso thing is and the Polar language and sort of various pieces around this, like the Oso libraries, and following that, I'm going to dig into like how we built this Oso Rust crate. And basically, what this all touches on is really what we needed was Rust to behave more dynamically, and we'll see what I kind of mean by that in a sec. Okay, so the short of what Oso is. So Oso is a policy engine for authorization. It's fully open source. It's available in multiple languages. The core of Oso is the Polar language, which is a declarative logic-based programming language with object semantics. And so what we see at the top here is like a snippet of that Polar language. So imagine you're you're trying to express your authorization logic. You write those in these rules. So for example, in this policy, you'd say, allow a user to read a particular expense, and then what follows would be the conditions for which that's true. So in this case, we want to make sure that the user's email is equal to the person who submitted the expense, right? And so like this is all sort of declarative and logically based, and some of the elements I spoke about, the object semantics, this might look familiar in Rust kind of syntax. We're actually checking that input, the input user type is a user object, and that check is the user object from the application. This is going to be like a pretty important theme that I keep coming back to. Similarly, when I do user.email, that is like the language semantics there is meaning pull that email attribute off of the user object and compare it to the submitter field attribute, pulled off the expense. And that's kind of all happening in the host language in the application, even though this policy is written in this Polar language. So then the idea is like in your application though, so like, okay, so in the policy, you express all your authorization logic. And then in the application, you just make a simple call to the Oso policy engine, say, can this user read this expense? And again, those are just like passing in the Rust objects, the Rust structs to say, is this allowed? And the policies are acting over those things. Okay. So this is the kind of overview of the current system, the current state of Oso. So the language Polar, the whole thing is implemented in Rust. So that is this box at the bottom here. The language is implemented in Rust. That is potentially a topic for another talk another day, but the implementation of that is kind of interesting. And when we built this, we intentionally wanted it to be available across like multiple languages because we wanted this to be like a common way to write that kind of authorization logic in like any application. And that was one of the reasons we picked Rust, is because it gave us pretty good options. So we have a C API which allows us to kind of like link it into applications that support C in a kind of reasonable way. For the case of like Node, we actually use the kind of WASM stuff, which is pretty nice. And then the Rust OSO library just pulls in Polar as just a regular crate. So that's kind of like a high level view of what's going on. And really, this is kind of, this setting is like motivates a lot of what's like going on. All the stuff I'm going to speak about is this idea that we wanted to have a like language abstracted away from applications that you could use across any application, any language. But to be able to like have that separation, there's a bunch of stuff you need to do, and that's kind of the stuff I'll talk about today. So yeah, as I said, I'm going to focus mostly on the the OSO crate. A lot of the content I'm talking about today is kind of pieces that I've taken from this kind of like ongoing series, the blog series we've been writing out, where we've been sort of laying out some of these pieces we had to build. So if you want to kind of like after this, go and read some of these in more depth and see these examples, they're all available in the blog posts. And the third and final part should be coming out soon. Okay, so that was kind of the brief overview introduction. I'll kind of show you a little bit of what this looks like in Rust. All right, so I'm going to be doing this meetup in, there's a Jupyter kernel that someone built that you can use Rust in, which is pretty cool. It's Jupyter EV-CXR, I think is the project. It's super cool and it actually works really nicely. So, okay, so here I have a little code snippet. So this is me effectively importing the OSO crate. I'm creating a new instance of the OSO policy engine, and I'm writing some of my Polar rules that I want to load into this policy engine. So when I run this, so what this rule here is saying, for example, the same syntax we looked at before, I have a rule which is element in list, and it takes as an input an element. This is just a variable effectively. And it's saying this is true if the element is in this list, which has 1, the string ABC, and a dictionary with a key B and a value 3. So, I've loaded this into my OSO policy engine. Now I can query it. So in this first one, so in this first one, the syntax is I'm querying for this rule, and I'm passing in as the input. It has to take in a tuple, but it's taken in effectively the one tuple, which is 1. And we're looking for the next result, and we're seeing this is like, okay, so the kind of the first thing to point out is, this is like, because Polar is a logic-based language, instead of it being kind of like calls and returns, you're sort of querying it and you're getting results back. And so you can have like 1 or many, or 0 or 1 or many results that come back from this. In this case, like there could be more information down here. We'll see in a sec. Similarly, if actually I'm going to hide all these spoilers. There we go. Let's make sure these are run again. Okay, so in this case, right, so I passed in the value 1. 1 came in as an element, and it just checked that, yep, 1 was indeed in this list. In the second one, I'm going to pass in 2. 2's not in the list, so the result is just none. There were like no, the policy engine decided there was like nothing made this true. Okay, but logic languages can do a bit more than just like these sort of yes/no questions. The kind of idea is that I don't even need to pass in a value. I can pass in a variable x. And in the case of this one, what we're going to see will actually get back. And you can kind of see I'm like pulling out all 3 results. And I actually get back like every single result, right? So I get back an integer 1, I get back the string ABC, and I get this map back. And so this is us like getting back. You can kind of maybe see from some of this like Polar value stuff. We're getting back values from the policy that we've queried for with those variables. Okay, so that's like the do I want to show this now? Yeah, so this is like this is us like querying the logic programming language, and like at this point it's still debatably useful. Logic programming languages are kind of cool, but I'm doing some stuff with like checking in lists, and I've got this like basic interface where I can pass back types, and I can pass in integers, I can get back strings, stuff like that. But the thing I alluded to at the beginning, which is where this gets like super powerful, is that you can actually write those policies over your application types. So here I have a very, very simple example. This is stuff I'm going to dive into in a sec. So I have a regular Rust struct called cat, and I've derived polar class for it. And what this gives me the ability to do is register this on the OSO policy engine as a type that the polar language now like knows what it is. So in this case, right, I can write a rule which is say this is a cat. So it's basically type checking here that the thing I passed in is indeed a cat. And again, this is all like happening on the logic side, on the polar side. So let me just get that one running. So then again, I'm just going to query this rule. This is a cat rule, but I'm going to pass in 1. And the point is this is all happening dynamically. So I can have like multiple rules. In theory, right? I could have another rule which is just like doesn't even check anything. And this would then succeed. And the idea is like multiple rules effectively works like an OR. So you can actually have like multiple rules for different types and have like different sort of method, kind of like a method dispatch type thing based on these type specializers. And kind of as we'd expect, right? If I actually pass in an instance of cat, this is something that the policy engine is able to handle and can actually somehow type check, and it comes up with like, cool, this is okay. So this is like, very kind of quick intro into like what the OSO language. As I said, like the main use cases we've currently targeted for this is for writing authorization logic. The idea, passing in a user object and a thing, piece of data that someone's trying to access and deciding if it should be allowed. Which is like a really nice one for this kind of logic, because that often like comes into this like forked if-else logic. If they have this role, if they don't, like things like that. But really, the kind of the thing I want to get across is this is just like a general language. Okay, so how did I manage to just make Polar, the language underneath all this, be able to check whether the thing I passed in was a cat or not? And similarly, how could this work in Python and Ruby and Java and Node and all these kind of things? Basically, what we need is this like concept of runtime reflection. We need Rust to be able to be more dynamic. Like if you've worked with something like Python, you can do things like is instance and check whether this is the right instance or not. But that kind of exists in Rust, we'll see. But like there's actually a whole bunch of stuff we let you do. We let you pull attributes off and call methods, which like Rust doesn't have this kind of concept of reflection, something like Java or Python does. So these are kind of the 3 areas we broke it down into that we need to implement for this. So, okay, yeah, so dynamic classes. And the kind of main thing here is again, this like kind of type checking, like how do I make sure the thing I pass into a rule is indeed a foo or something? So the main piece of this kind of already exists in Rust actually, which is kind of nice. There's this any trait, and basically it actually kind of lays it out right here in the docs. A trait to emulate dynamic typing. So, Rust doesn't have a concept of classes, but it has something pretty similar. It has structs, it has impls, and the two together is kind of like a class. And this any trait, sort of works like that. Bottom struct almost that like everything effectively is. So this kind of gives us all the pieces we need. I'm going to come back into my Jupyter kernel. So for example, suppose I just have a string of all things. I have a hello world string. I can take that, a nicely properly typed Rust object, and cast it into a trait object. So this box any is kind of like a trait object. It no longer has that concrete type. It's sort of just something it's known just by its behavior. All we know it's behind some kind of a pointer basically, and it implements the any trait. And so once I've done this, once I've converted this string into a box any, like I can't do things like print it anymore. It's not a string. It's like the type has been forgotten. It's been thrown away. It's now an any type, and it doesn't implement display. It implements type ID. This is the kind of only thing you really get from it. But I can get my string back, more or less. I mean, I can get my box string. I put it in a box, and it's still there. In this case, this is using the downcast method, which is actually a member of box, but is deferring to the the any tree. Well, actually, I won't pull it up. Downcast is implemented for box any basically, and what this is going to do is at runtime dynamically check whether the thing inside the box is in fact a string, and it actually returns a result. So like if it succeeds, you get the string back. If it fails, you just get back the original box any. And so in this case, you can see I've taken my any, I've downcast it back to a box string. And now I can just call things like, make ASCII uppercase on it. I can print it out again. I got my string back. And this is basically like the main, this is like the core piece of our like class implementation. So basically the way we've implemented dynamic classes inside Rust is like these two pieces. There's like the class, which is the thing that stores all of our information about the type, the name, the type ID, the attributes it has, the methods you can call on it, all of that sort of information about what it can do. And the instance, which is basically a wrapper for that any type. I can kind of show a little bit of this. So here's my class structs. As I say, it's got things like the name, type ID, constructor, like all of the behaviors defined on the class. And then the instance has that inner, in this case, an arc instead of a box, but very similar, this reference to an any type. And that's kind of about it. So it's just, types being arrays. And then if we want to do anything with it, we need to reference that class and ask the class like, okay, how can I do something with this? And so, for example, we have a simple test, which shows this in action. I have a foo, I have a bar. I define the foo class using the class builder and the bar class. And then I make an instance of, I take foo and I make it into an instance. So this is now like, type forgotten. And I can now ask like simple questions. This is kind of like an internal piece. I can say, is this foo instance an instance of the foo class? And it shouldn't be an instance of the bar class. And like, there we have it. We have like dynamic classes. These are now, this is basically the core thing that's powering those like specializer checks. So that's kind of the dynamic classes. But those by themselves are like not that interesting. Like a little bit of type checking doesn't go too far. Like what you really want to be able to do is like start reading things like attributes off them. So you can start, adding those in your rules and your policies. The reason, so this one isn't as easy. There isn't anything built in intrinsically from Rust which lets you just do this. And I think the reason for this is kind of this little piece I pulled from the reference, which is if you take just a regular Rust struct, Rust gives you sort of no guarantees about the fields of that struct being in any order whatsoever, because it's free to like rearrange them for optimization, which is actually one of the coolest parts of it, right? Like if you don't need to think about layout or like rearrange them and make it nice and compact. You do have options to avoid this. You can tell Rust like, no, I want this to be laid out like C would do it, and then you can do point arithmetic and offsets to work out where the fields are, but you don't get that by default. And we wanted to avoid like having that as a requirement that people would put repr C on all of their Rust structs. We looked at a bunch of different approaches, and in the blog post I kind of shared earlier, like we sort of went through, evaluated each of these and which one makes sense. There are traits in the standard library that kind of look like they'd work, like this index one, but it forces the output type to always be the same. So you kind of don't necessarily have something that works there. Serde is very, very good for this kind of like data transformation type thing, but we didn't like how it was kind of conflating the idea of data formats with like application objects and things like that. And ultimately what we came down to was this idea of just having attribute getters. So one of the things we stored on that class was this attributes map, which takes you from the string name of an attribute to an attribute getter, which is more dynamic arc thingies, which is basically we store a function that takes in that instance and will return a value. And so what this looks like is like this. So okay, so now I have a struct with I have a foo struct, but this time with an X field on it. And when I define that foo class, I have like additional helper methods I could build on it, like this add attribute getter. And so I'm basically saying I want X to be accessible dynamically, and the way you get X is through disclosure. There's a foo and just do foo.x. And now with this in place, you can write rules like this little inline rule I've got here, which is saying checking that foo.x equals 1, and if I query the rule for foo with x is 1 or foo with x is 2, I get some or none. So that was that was kind of pretty nice. One of the I think there's something quite nice about like how simple this syntax is, and like if you could actually add attributes to your struct that don't even exist. It'd be kind of interesting. One of the nice things about this as well, though, is it's like because it's so simple, we actually support this directly through the derive macro. So you can also just annotate polar attribute on a field, and it'll just basically do this bit for you. Okay, so that's oh, and yeah, I think the kind of some of the nice patterns to look at here, right? So like this, the attribute getter thing that we store, again, it's operating over that instance we saw earlier, and basically we, somewhere between passing in a closure that takes a foo and it again stored on the class, like we effectively just have like a few places where we get to do those like little shim layers where we get the instance, we downcast and at runtime type check that where did it go? We're type checking. We're actually doing some type checking here at compile time, but also like at runtime to make sure that we, there's nothing kind of crazy going on. If I tried to make this, if I passed in some weird closure that took a bar or something, or maybe just like a string, and I try to run this, should work. It's just not. Let's just return 1. What's kind of nice is that we're going to get like a type error because it's expecting a function that takes it a foo. So it's actually kind of hard. It's kind of hard to get these things wrong. It's kind of like a little bit of user experience thing there. So dynamic methods. So these are where things get really, really interesting and really takes you into some of the sort of complex areas of Rust. So to start with, right, the setup we had for attribute getters actually makes a lot of sense. And if all we cared about was methods that didn't take any arguments, we were done. Like, and actually in some languages, those two things are basically the same. Like in a Ruby, there is no difference between like an attribute getter and a method. They're basically the same thing. We would be done. But the key bit that we needed to add was this ability to take in, a list of arguments from the polar side of things, right? We don't know. This is like another piece of dynamicism. We don't know exactly how many arguments are going to get passed across. And the problem is like there is no like currently there is no Rust trait which says a function with any number of arguments. So we kind of needed something like this. So this was our first attempt. We were saying, okay, I need a function, and I basically want to invoke it on a list of polar values. And we can do the conversion down in the implementation, for example. But how we would want this to work, though, is that for every function that has, I'm actually missing some types here. I think I've got this. Here we go. This one's better. What we really want is that like every Rust function is just going to work like immediately as this new type of function we have, and we can do a little bit of the conversion stuff like inside the implementation. So here's the example for like one argument. So I have a function. I have f, which is a function from a single argument a to r, and actually I should have a is like from polar value or something, from polar. So we can do this down here. I think I don't need this for now because it's going to fail anyway. This is what we wanted to do, right? So like blanket implementation for this new trait for any function, and we'll do this argument conversion for them, and everything will just work super nicely. If you try and do this though, you get this error, which took me a while to really get my head around exactly what the hell this unconstrained type parameter thing was, and I feel like it comes up a bunch. And I thought it might be interesting for people to kind of like go a little bit into this specific error, like what this means, because I think it is one that comes up a lot, and it's like not clear what it is, because it's like the type parameter a is not constrained by the input trait, self type, or predicates. But it's here. Like I can kind of see it's constrained. I can even write a from polar. Like that's not going to make a difference. Like why is this not working? And basically the thing that's going on here is it's kind of hard to see it in a function one, because you really think about a as being like inherently part of the trait here. The thing to notice is that like in theory this trait could be implemented for, you could have multiple implementations of this trait for different values of a. So imagine I have foo, which takes in a generic parameter x or something, and returns whatever u32 and just returns 1. This does indeed implement fn a to r for all values of a, for all values of x and stuff like that. So that seems fine. But imagine if I gave, if I passed in, if I was Rust and I was trying to work out how to dispatch, like how to actually call this actual body, I sort of need to know which value of a you want me to care about. And it's sort of awkward that it exists for functions, but I think it's maybe more obvious in the case of some of the other. Do I have no, I don't have an example down. In the case for other traits. So I'm just going to start off with just an empty trait, and I want to say impl for t, and let's say for all types t and u that implements from t. I want to implement my trait for t. Right, like imagine I have like a string, and I'm trying to say like string as my trait, and do something with it. Like, how does it know which value of t this is? This should be for u rather. Right, there's no way of Rust when it's like trying to dispatch string as an implementation of my trait, which value of t it should be using. It like, it's kind of like the implementation is just asserting that there must be some t that u implements from t for, but after that point it's kind of lost, it's lost to history or something. And this could actually be impactful. Like if this has some method that depends on that depends on t somehow, like maybe it's like get type ID, for example, and this returns Rust type ID. We have some trait and it's asking for the type ID, and our implementation of this is going to depend on that value of t, right? So this returns a type ID, and this does like standard any whatever type ID of t. Again, like if I just have a string, yeah, string implements from string implements from referenced or whatever, like implements all these various traits. Like how Rust can't know which value of t you expected this to work for, and there's no way of me saying like string as from t, like this isn't a thing.
Hey Sam,
Yeah.
there's a hand raised if you want to field the question right now, or you can
Oh, I'd
keep
love to.
going.
Yeah.
Hey, thank you. Can you scroll up just a half page? So here you say invoke. It takes a vec of polar value and it returns a result. No, so polar value, that's kind of like your dynamic class, or kind of your single type.
Yeah, exactly. So polar value. So when earlier I returned like an integer, a string, and a map, those are all enum variants of this polar value enum.
How does that differ from self result?
Self result here is whatever the function returns.
But wouldn't the function return a polar value?
We'll actually want the function to return something that can be converted back into polar. So basically the desired functionality here is that you give me a function, and as long as the inputs as long as the input types I can get to from a polar value, right? So I'm like in the polar VM, and I got some types I'm trying to call this function. I give you polar values, and you can convert them to the input types. You can call your function and then return a type that I'm going to then convert back into polar values.
I see, but you don't necessarily want to lose the information that I gave you a specific type, so that's why you have this result. You want it to be convertible to a polar value, but you don't want to necessarily like lose the information just by immediately upcasting it to polar value, basically, right?
I totally could actually. I could do this dot to polar instead, and this would be polar value.
Right.
And actually, I think that is roughly what our implementation looks like now. It's been through a few iterations.
I was just wondering what the upside there is. It seems like maybe you get more information out of the function, like it's more constrained in its outputs, or in some way.
There is actually one case where this matters, which is for constructors, because constructors, we know that we want to return back the like original type and turn that into an instance. It like has a slightly different flow. but yeah, these are all things that they're going to happen at some different layer, and like whether it happens in the blank implementation or for us, we like have a a wrapper method that will do the conversions outside it. It's these these things they move around a few places a little bit, but it doesn't change like the core bits of this.
Awesome.
Yeah, but yeah, you need like these two constraints on like the inputs and outputs.
Thanks.
Okay, so yeah, I'll stop going down this route. But yeah, it's just basically, so the version of this, so yeah, hopefully that made some sense. But yeah, the idea is, if these, because these types don't show up anywhere else, like you sort of lose that information. And it's true again in the case of function, which is like, f doesn't necessarily know which value of a you expect this to be implemented for, so it doesn't have to do this conversion, is why it has this complaint about type parameters. So there's a couple of things you can do to address this for functions specifically. You could, instead of implementing this for the trait, you can implement it for like the function pointer. So this is an actual concrete type effectively. Instead of being a blanket trait implementation, this is a concrete type. The unfortunate thing about doing this, and we'll see it kind of down here. And again, this is like another one of those corners of Rust that I actually found was like very, very poorly documented. It didn't really find this anywhere, so I was kind of interested in what was the reason behind this. So I have just this like whatever trivial my trait, and I've implemented it for function pointers with argument a and also like dynamic functions. So here I am trying to cast I'm trying to cast a closure which just takes in a single value x as an implementation of that trait. But it didn't work because it's saying my trait is not implemented for this interesting looking closure expression thing. And so basically what's happening here is like this, closures all have their own distinct types. And it's like this name you can't really reference. It's an anonymous type. You can't reference it anywhere, but it has its own type. Okay, so what about if I try and do this with like a proper function, right? I have this test fun. It just takes in a single value. And again, I'm going to try and do the same conversion. This actually doesn't work again for almost the same reason. But the output makes it look like makes me feel like this should have been fine. This took me a long time to work out what was going on here because I was like, this, fun U32, that looks like it should match and so on and so on. But the important bit is this like bit in the curly braces, because when I reference test function here, again, it actually has its own distinct anonymous type. You can't actually reference it, but it is kind of like written like this way. And there's actually a difference between the function type, like the item function item, and a function pointer. And it's basically a pointer dereference away. So to make those two work, what you'd actually have to do is coerce them to function pointers. And so both closures and functions can be converted into function pointers. Both of these work fine. And basically it's just you have to go this like extra step because under the surface, what's happening to go from a function pointer back to a closure or back to an actual function is you're reading the pointer to find the address. So you can actually see if you go on Godbolt, like the additional instruction that's happening. And so the reason we didn't want to do this, we weren't happy with this because it meant that whereas before when I did add attribute getter, I just had like the closure, the user would have to write as fun blah after like every single method they added, and that was just like for us not acceptable way of exposing this. So basically what it turns out, the way to solve this problem, the sort of correct way to solve this problem is to move the types you need, move the types you want to reference onto the as a generic on the trait. And it's actually kind of the more correct way to do it because we want to know the args the function has. So we saw that one. Yeah, this was I don't know, attempt number something or other. You can tell I've gone down and covered the rabbit holes here, but this is what it looks like in the end. And basically the only difference we had to do was add the args up here. Nicholas, related to your question earlier, we at that point we actually were like, well, we don't even need to care about doing the type conversion stuff in line. We'll just keep this function as a pretty nice, like high level, just Rust trait. And the nice thing is this function trait is actually very, very similar to, there is actually an unstable Rust feature for function traits, which has the format. So instead of, undo this, instead of this format, it actually has the format like fn with the braces that you normally expect in a trait, and it takes in a tuple. So it would look like this, and it has a result type. So we could have written this kind of thing. So this is this is again an unstable feature, but this is basically what we ended up with in our traits. There's a few other things that are happening here. So we have a function one and we have a method one because we wanted to be able to support both pure functions that we call without a self type. And that's kind of what this receiver is here, but also like methods on an instance. So we already have a foo. We want to call a method on a foo instance. And unfortunately, there's like there's kind of some limitations in how you can like unpack tuples in traits, in Rust traits, that we couldn't write a version which was like, method is just a more specific version of a function where the first element of the tuple is the receiver. That's like not a thing that existed. Yeah, before I move on to that, and basically the stuff that's kind of supporting all of this. So we have this in method. So we have our traits, and basically what we have to do is implement them for all possible tuples. We went up to tuples of length 16. This is a pattern I think you get quite commonly. If you ever go into like a Rust doc and you just see there's like thousands of these implementations, this is probably why, something like this. So we have some nice macro business going on here, which is unpacking the args and just calling the function on every arg. Yeah, it's as simple as that. Like, the difference here is just this pair of brackets. So it'd be nice if Rust stabilized this. And then the piece that makes this really like nice from a user perspective is we have like an instance method wrapper. So this takes in a method, right? So you just make sure that you have a method with the receiver type T and some args. The args need to be, all of them need to be from polar, and the result needs to be to polar. And we'll handle all the other details. So we'll make sure that, we'll go from the instance, we'll downcast it back to the type T. So again, like coming back to those like original type checks we had, like the method you pass in has to be of the right type, and we'll downcast it. We convert all the arguments, we call the method, and then we convert the return type. So all this is kind of like happening, hidden from the user. And I can scroll down, and and so this is kind of what it looks like in the end. So all of that works so that we can say, if I have a method like add things, it's got a self, takes an argument, I can add that method onto my definition of a bar class. This I was pretty happy with. Again, so this is where I don't need to do as fn, and bar blah u32. Like I don't need to do this for everything I write. I can just use the sort of proper Rust method syntax to pass it in, and then I can call it. So that's like those are kind of like the main pieces. There's like a few other like interesting bits and pieces that happen through this, which because of the time I won't go into unless people are interested. I can maybe do as a follow-up. So we implemented class methods, and there's some really nice tricks we do with class methods that we borrowed from Python, which is that we actually registered the class as a class. So this like actually, I guess it's in my thingy. This class struct that is our like class that stores all the objects. We registered this itself as a class, so that when you call a class, you call a method on a class, you call the class's class method, which is kind of like a nice little trick. And we also support things like iterators in Rust, but iterators in results. But the results was okay. We just kind of you can convert. It's kind of like all handled kind of somewhat invisibly, but iterators were particularly difficult because and we had to like add an additional method so that we would like wrap the return of an iterator in our own iterator type that we could iterate over, things like that. This kind of stuff is actually, the stuff I've been walking through isn't as unique as I expected when I started out. It turns out like building some kind of embedded language in Rust is a pretty popular thing to do. So there's actually some really great other projects out there for just like general purpose scripting languages as opposed to like logic ones, which were pretty great for inspiration. You see a lot of commonalities. They all define some version of this like function trait, things like that. I want to call out like the Rust bindings for Python interpreters as well, because they do a lot of this like dynamicism. So yeah, I mean, that's the main stuff I wanted to go through. If you want to learn more about OSO and what we're up to, probably a good place for that is the website, where you can find things like the blog. Absolutely everything we're doing right now is open source. The language, the Polar language at the core, all the libraries. You can see 200 CI jobs we have to build this for every language and platform and all that kind of stuff. And yeah, we have a Slack for anyone who wants to come and talk to us about Rust, the stuff we're doing, authorization, security, anything in general. And yeah, I'm happy to take any questions people have. Oh, and I'll pause the recording there for people if I can find the button.